Okay, folks, I'm going to erase this because I don't want you to see this, but I did start this video before and I had a technical glitch with it. So rather than erasing everything and trying again, I'm just going to walk through this. We are continuing in our study about work and energy. And we learned in the lesson yesterday that work acting on an object gives that object energy. And then that object that has energy has the ability to do work on something else. So work and energy flow in and out of each other very easily, almost spontaneously as objects interact. So we talked yesterday about what work is and how you quantify it. Then we said this in the energy portion of it, there are four forms of energy that we're going to look at, and we're going to study them more in detail as we go along. And then at the end of the chapter, we're going to take the idea of work and energy and put them together into one equation. So right now we're just learning the pieces. Eventually we will figure out putting them all together. So we started talking about the derivation of kinetic energy, how that formula can come about mathematically, and you should know that. Make sure that you're working on that. And then we're going to talk now about the formulas themselves. The kinetic energy of mass m moving at speed v is Ke is equal to 1/2 mv squared. Notice that this is Ke and not delta Ke. It's just the kinetic energy an object possesses because it's moving. If I'm changing the kinetic energy, what is the factor that I am actually going to be able to change along with the changing kinetic energy? Do I change the mass of an object or do I change the velocity of the object? And if you think it through, it's obviously going to be the velocity. So this is the equation I use when I have a constant velocity. I will use the delta Ke equation when I have a change in velocity. What would cause a change in kinetic energy? Newton's law says an unbalanced force is what is going to cause acceleration. So work has to be done, or force has to be applied to it in some way. It could be a force already built into the system, or it could be a force from outside the system, work being done from outside the system, causing it to accelerate. If I change the velocity, then I end up with v minus v naught. So delta Ke is that I'm having the speed of the mass change, not the mass itself. Excuse me. How do I end up with that equation of v squared and v naught squared? Delta Ke, delta anything, is final minus initial. So if I have delta Ke, then what I really have is Ke, 1/2 mv squared, minus Ke naught, 1/2 mv naught squared, because again, only the velocities are changing, which is equal to delta Ke is equal to 1/2 m v squared minus v naught squared. So this is another way of coming up with this equation of delta Ke. The derivation is what allows us to jump into kinetic energy without any prior knowledge. This equation comes from this equation. All right, now let's talk about how we're actually going to use this equation. If I have kinetic energy, it's just a constant velocity. If I have a change in kinetic energy, then my velocity is changing. So for the problem 8.3, a 0.1 kilogram stone is thrown from the edge of an ocean cliff with an initial speed of 20 meters per second. When it strikes the water below, it's traveling at 45 meters per second. What is the change in kinetic energy of this stone? So I did my drawing again. You'll notice here, drawings are awesome. You can't always do them, but boy, whenever you can, I want you to. This is a case where you can do the drawing. Notice that the stone was thrown and not dropped. Because it was thrown, it has an initial velocity of 20 meters per second. It hits the water at 45 meters per second. I have all this already drawn. I have all the numbers and everything put in. Feel free to pause the video so that you can keep catching up with me as I go. Please notice that I don't really care that it is making a parabolic motion as it goes down. It's not projectile motion is probably the more common way of saying it. I don't care about that because kinetic energy does not depend on direction. It's a scalar quantity. All that matters is my initial and my final velocity, not the direction of them. So don't worry about the fact that I have a projectile motion kind of drawing in place here. So I have all of my numbers put in, and I'm going to just go ahead and apply them to the equation. 1/2 mv squared minus v naught squared. 1/2 0.1, 45 squared minus 20 squared. You do all the math on that, and you end up with 80. And of course, I've already learned that the unit for energy is the same as the unit for work. Work and energy flow in and out of each other, so they have to have the same unit, and that unit is joule. But it seems like a big leap to go from all of these units that I have at the start to this unit at the end. So my equation basically that I care about is the kg. The 1/2 does not go into making the units. I'm sorry. I really only care about, I'm going to start from the very, very top here. I care about my mass times my v squared minus my v naught squared. So I'm going to deal with the units for those. But here's the interesting part about this. V squared minus v naught squared will all combine into one unit. And I want you to think of it this way. If I have a length of ribbon that is 10 centimeters long, and I cut off 2 centimeters, how much do I have left? In your head, you're doing the math of 10 minus 2, or 10 centimeters minus 2 centimeters gives me 8 centimeters. Centimeter minus centimeter is just centimeter. If I have 4 quarts of milk and my dog eats 1 quart of milk, then how much do I have left? 4 quarts minus 1 quart, I have 3 quarts. Quart minus quart is quart. All of that to say that this unit minus this unit is going to be the same unit. So I can just do this, m times v squared, because it's going to end up being the same unit if I subtract it. So I don't have to worry about that second one. Now let's put the units in. Unit for mass is kilogram. Unit for velocity is meters per second, but I square it. Now what I have is kilogram times meter squared over second squared. That's still feeling like a long way from joules. But I'm seeing something vaguely familiar in my kilograms times meters per second squared. If I pull that out, kilogram times meter per second squared is actually a Newton. And when I pull it out, I'm left with a meter. When I pull a meter out of my meter squared, I still have 1 meter left. So this whole thing becomes a Newton times a meter. Oh yeah, that's the definition of a joule. So legitimately, my answer comes out in joules. All right, now let's look at number 18. And if you need to go through that again, shut the video off. Try coming up with that again on your own. That's actually an important piece of information. You need to know where these units come from when we end up with joules. How is that possible, and is that legitimate? You need to be able to prove that to me. All right, so looking at number 18 in the notes, huge amounts of air circulate across the Earth in regular patterns. A tropical air current called the Hadley cell carries about 2 times 10 to the 11th kilograms of air per second past a cross-section while moving toward the equator. The average airspeed is about 1.5 meters per second. Calculate the kinetic energy of this moving air. Notice that it's asking for the kinetic energy, not the change in kinetic energy. So please write down your knowns and your unknowns. This is one where it would be very difficult to draw moving air. So I'm just going to have to go with my knowns and unknowns. But anytime I can draw, I'm going to draw. So I'm not looking for delta KE, I'm just looking for kinetic energy. So my formula is KE is equal to 1/2 m v squared, and I end it with that. 1/2 mv squared ends up being 1/2 times 2 times 10 to the 11th times 1.5 quantity squared. I do the math with that, and I end up with 2.25 times 10 to the 11th joules. And you'll notice my units are going to be the same, because here, instead of having v squared minus v naught squared, I just have v squared, which is the way I calculated it up here anyway. So we've got joules, we're comfortable with that, it's going to work out just fine. Now, the next part of the question is letter B. The United States in 1980, this is old, the United States in 1980 used about 7 times 10 to the 16th joules of energy. Calculate the ratio of the kinetic energy of the 2 times 10 to the 11th kilograms of air of the cell that passes toward the equator each second, and the total amount consumed in the United States each second. Now you'll notice that what they gave us was the amount that was used in 1980. So that was in the year 1980. So we're going to have to do some dimensional analysis with this. So what I know is 7 times 10 to the 16th joules in the course of 1 year. But I know that 1 year is 365 days. I know that 1 day is 24 hours. I know that 1 hour is 60 minutes. And finally, I know that 1 minute rather is 60 seconds. So the total amount used, it was this much in a year. In a second, the conversion is going to be 2.22 times 10 to the 9th joules per second. And this is joules per second as well because it's meters per second. So this is joules per second. This is the number of joules that is used in every second. So I'm comparing the two of these. And you'll notice that this part of it and this part of it are almost exactly the same, close enough. So what I'm really going to compare now are my powers of 10. This is 2 powers of 10 greater than this. 2 powers of 10 is 100. So the Hadley cell is at that point was 100 times more than what the US used per second. Okay, so the ratio would have been this ratio to this ratio, 100 to 1 essentially is what it works out to be. All right, that's just a little dimensional analysis to make a comparison. Obviously, there is a truckload of energy in that air cell. If it could be somehow harvested or the energy taken out of it and utilized, that would be a big boon for society. But so far, that hasn't happened. And we'll talk about wind energy at some point when we talk about electricity. Wind energy is awesome. It has its drawbacks, and we'll talk about what the drawbacks are down the road. All right, the next thing I want to talk about is gravitational potential energy, or PEG. By the way, your homework over the kinetic energy is going to be 12 through 14. And then also, I'm going to have to get back to you on that one actually. 12 through 14, I know for sure. And then I am not positive after that. So let me get back to you. All right, gravitational potential energy. Where does potential energy of a raised object come from? If I have my pen here, right now it has no potential energy compared to the desk. If I raise it up to here, I don't know if you can see, if I raise it up, how did the pen get gravitational potential? It got it by the fact that I applied a force over a distance. In other words, I did work on it. So where does potential energy come from? From the work done in raising the object. Now we're going to set up a derivation again, so I need a situation where all the work goes into changing delta PES only. So what I'm going to do is I'm going to lift, just so I can get all air resistance out of there, I'm going to lift an object in a vacuum. There was no spring involved. There's no delta KE. Even with my pen, in this system, there is no delta KE. What is my kinetic energy at the beginning? 0. Now it's my kinetic energy. It's 0 again. What is my change in kinetic energy? My change in kinetic energy is 0. So if I lift it and stop it, my delta KE is 0. It's in a vacuum. There's no friction. And there's no spring. So I'm good. So the beauty of that is all the work is going into changing my gravitational potential. So this is my given. Remember, we have to have the givens. Now, I'm going to start you out fairly easy with this. We've already done the W is equal to F delta R cosine theta. We're just going to jump right into W is equal to F times D. My reason for that? Definition of work. Now, ultimately, I want to end with delta PEG is equal to mgh. Now, h, by the way, m stands for mass, g stands for acceleration due to gravity, and h is the height that I've lifted it. I want you to work through how would you get from the F and the D down to this. What process would you use to get there? Pause the video, come up with as many of these steps as you can. Okay, let's get back to this. So the first thing I'm going to do is I'm going to address my D. My distance that it's traveling is actually the height that I've raised it. So my D is equal to h. How come I can say that? That's my given. My given is that I raised it a given height. I lifted it in the vacuum. So my D is height. It's not going to be something horizontal. It's going to be the vertical separation. That's my given. That's what I did. All right, so that already takes care of the D. That's actually pretty easy. Now my force is equal to the weight. Because I am lifting just that object, the only way that I can lift it up is if I overcome its weight. And so that also is a part of my given. I have lifted up an object. The way that I lift it up is by compensating for its weight. I'm now going to say that weight is equal to mg. That is the definition of weight. So now I have F is equal to weight, weight is equal to mg, so I can say now that actually my force is equal to mg, and that's the transitive property. A is equal to B, B is equal to C, A is equal to C, transitive property. A is equal to B, B is equal to C, therefore A is equal to C. A is equal to C, transitive property. All right, so now I can actually say that W is equal to mgh because my force is now called mg, my distance is now called h. That is pure substitution. And the only thing that's different now between this and this is I need to get my work to equal delta PEG. And I can say that because all of my work went into changing the gravitational potential that is given. I get from here to here by substitution. You also could use transitive property for this one, but I'm okay with you using substitution as well. All right, so this is how we get from W is equal to FD down to delta PEG is equal to mgh. Be working on these. I would just get out a note card, write your first statement, and see how you do getting down to your last statement. Again, you're going to need to note these. I will put into PowerSchool what the homework is for this chapter, so be looking for that in the assignment part of the page. All right, let me know if you need anything.